Welcome back. This is the class video that goes with video lectures 16.1, part 1 and part 2. We're going to practice with the ideas that we introduced in those two video lectures, where we focused on transverse, sinusoidal, traveling waves. And we're going to just practice with those ideas. In all the class sessions we have, I like to start with learning objectives. Sometimes certain sections have a lot. Chapter 16, Section 1 on transverse waves has a lot of learning objectives. I'm going to highlight the ones I consider to be the most important. 16.1.2, distinguish between transverse and longitudinal waves. At least just be able to tell in words the difference. A transverse wave, first of all, in our mechanical waves are disturbances on some kind of medium, material. In a transverse mechanical wave, the disturbance of the medium is perpendicular to the direction in which the wave travels. Transverse wave on a string was our focus in the previous lectures. In a longitudinal wave, the disturbance of the medium is in the same direction that the wave travels. We'll study that in chapter 17 when we study sound waves. Next, 16.1.3. Given a displacement function for a transverse wave, determine its amplitude, angular wave number, so amplitude y max, angular wave number k, angular frequency omega, phase constant phi, and direction of travel. And calculate what's called the phase, which is that combination, kx plus or minus omega t plus phi, and the displacement at any given time and position. So what he's talking about here is using the wave function that I introduced in the previous lectures. Y of x and t equals y max sine of kx. I'm going to write plus or minus omega t plus phi. Now, this argument inside the sine function, the whole thing, kx plus or minus omega t plus phi, is called the phase of the wave, or of the wave function. That's all that means, is that argument. The plus or minus is important to keep track of. It's one or the other. That's just a way to talk about two situations. Either the wave is traveling in the plus x direction, or the wave is traveling in the negative x direction. Remember that if the wave is traveling in the plus x direction, you use the minus sign. And if the wave is traveling in the minus x direction, you use the plus sign. These are just opposites, okay? So that's what he means. He means being able to use that formula correctly. 16.1.7. Describe the effect on a transverse wave of changing the phase constant, phi. Well, the way I like to describe it is the phase angle or phase constant phi tells you at time zero how much your waveform deviates from being a simple sine curve. If it is at time zero, if the waveform is just a plain old sine curve, as you learned in high school trig, when you plot it, then the phase constant is zero. But if the waveform at time zero is a sine function that's been shifted left or right, then the phase constant is not zero. 16.1.9. Apply the relationships between wave speed, v, angular frequency, omega, angular wave number, k, wave length, lambda, period, capital T, and frequency, f. That's a lot, but they're all very simple formulas, and they're all very useful. I'll write it this way. The wave speed, v, is equal to the angular frequency, that higher up there, over the angular wave number. You can check that from the units. Omega is radian per second. K is radian per meter. You check those units simplify to meter per second. But you can also write this formula relating V and omega and K as follows. For the omega, put in 2 pi f. For the K, put in 2 pi over lambda. And you get another expression connecting v to other quantities, namely frequency f and wavelength lambda. V equals f times lambda. And if 1 over the frequency f is the period, so you can also write it as v equals wavelength over period. That's what that learning objective means. And then 16.1.11, calculate the transverse velocity u of a string element as a transverse wave moves through its location. Well, what he really means there is calculate u of x and t. And I talked about how to do that in the previous video lecture. You have to take the wave function for the wave y of x and t up above and do what's called a partial derivative of y with respect to t. That means take the derivative with respect to t and assume that everything else, y max, k, x, omega, phi, are all constant. And when you do that, you get plus or minus omega y max cosine of kx plus or minus omega t plus phi, where the plus or minus out front there depends upon which of the signs inside the cosine is the appropriate one. Depends on whether your wave is traveling in plus x or minus x. Well, let's get straight to some practice. Okay? What we have here is a snapshot at a particular time t of a sinusoidal traveling wave. We're told it's moving in the plus x direction and its speed is 2/3 of a meter per second. It moves 2/3 of a meter to the right every second. So we could just denote that maybe with an arrow to the right labeled v to remind us that this wave is traveling to the right at speed v, but this is a snapshot in time at some time t. Notice they don't tell me what the t is. Okay, notice the x-axis is in meters, the y-axis is in centimeters. The scales are different. And we're just going to we're going to go through these together, these questions. First question, what is the amplitude of the wave? I'd like you to think about that and really try it. Pause the video and think about it. When you're ready, come back. Okay, I'm going to write my answers either right up in this space or down below if I need it. Question 1 was, what is the amplitude of the wave? First of all, I want you to remember the symbol for the amplitude of a transverse wave. And use it, please. Y max. And what is the y max for this wave? Well, you got to look carefully at this graph and look at what the largest y value is for the wave. You've got to estimate it off the graph. And its peak is right halfway between 2 and 3 centimeters. So 2.5 centimeters. If you label the unit centimeter, you can leave it that way, or you can convert it to meters. It'd be 0.025 meters. That's the first question. Okay, second question. What is the wavelength of the wave? Based off that graph. Answer it for yourself. Pause the video. When you're ready, come back. Okay, first the symbol for wavelength. Please remember, lowercase Greek letter lambda. What is it? It's the shortest repeat distance. So let's try to get that from the graph. Let's pick a place that's pretty easy to identify. How about right there on the x-axis where the waveform cuts the x-axis going down? Then let's go out along the x-axis until we get to that same point on the waveform where the wave cuts the x-axis downward. So that next place where that happens is right there. So the horizontal distance between those two little tick marks is the wavelength. And you look very carefully, and the first tick mark is about at 0.4 meters, and it looks like the second one is at 2.4 meters. So the distance between them, 2 meters. We can it's probably okay to give 2 sig figs when you're using a graph, maybe not 3, but 2. So let's say 2.0 meters, okay? Right off the graph. 3, What is the period of the wave? I'd like you to figure that out, please. Pause the video so that you can give it a good try and then come back. Okay, how are we going to find the period? You're not going to be able to just read it off the graph because the graph is at one moment in time. And the period is an amount of time, a time interval. How about, however, if we use one of those simple little relationships that we just talked about, like frequency is speed over wavelength? That's an easy one to remember. But frequency is 1 over period, so 1 over period is speed over wavelength, or rearranging, period is wavelength over speed. And I think we know those things. We just found the period, the wavelength, 2 meters, and we're told the speed of the wave is 2/3 meters per second, and that turns out then to be 3 seconds. Okay? The period of the wave is 3 seconds. The frequency then would be 1/3 of a hertz, 1 over the period. All right, question 4. In what direction is the portion of the string highlighted in red moving? Moving when we took this snapshot. Which way was it moving? We've got 4 choices to pick from. It was moving in the plus x direction, the plus y direction, the minus x direction, or the minus y direction. Which one is it? The direction in which that highlighted portion of string was moving when we took the snapshot. Pause the video, get an answer, and then come back. Okay, first thing, this is a transverse traveling wave. So any particular piece of string moves, in this case, in the y direction, whereas the wave moves in the x direction. So the answer is definitely not plus x or negative x, because any particular piece of string is not moving along x, it's moving along y. The only question now is, was that little piece of string highlighted in red moving in the plus y direction, up, or the negative y direction, down? How can you possibly tell? 2 things tell you. 1, which way is the wave traveling? The disturbance, plus x. 2, where's the red dotted piece of string? Well, right there. So to figure out what that little piece of string element is about to do, look on the waveform at what is coming down the pike. And what's coming down the pike, if the wave's traveling to the right, is what is immediately to the left of this piece of string. And the piece of string immediately to the left of the highlighted piece is lower. So that tells me the highlighted piece is traveling down. Its transverse velocity, u, at the moment we took this picture, was down. Okay, so negative y is the answer. That takes a little getting used to, but hopefully you see what I mean. Let's go on to the next question, 5. Let's take as given that the formula for the displacement of the string is y of x and t equals y max sine of kx minus omega t. In other words, we're telling you that the phase constant phi for this wave is 0. So now here's the question. This snapshot that we are talking about, that you see here, was it taken at time 0? Yes or no? Think about it. Pause the video. When you're ready, come back. Okay. No, the picture was not taken at time 0, and here's how you would explain it. If we are given the fact that the phase angle is 0, then you can see what the waveform is, y max sine of kx minus omega t. At time 0, this term goes away. So you just have sine of kx. So if you plot it versus x, it's just a simple sine. A simple sine starts at 0 and goes up from there and oscillates like that. That's what the sine curve looks like. Okay? This plot doesn't do that. So all I can tell you is it was not taken at time 0. That's all I was asking. Was it taken at time 0? No, it can't be. Now there's one more question. Write down a formula for the displacement of the string at x equals 1 meter, t equals 2 seconds. Plug in all known values. So I just want to see if you can write down the formula. You don't need to go to a calculator. Write down the formula for the displacement of the string, the piece of string that would rest at x equals 1 meter when the time is 2 seconds. Pause the video, try that, and come back. So if it wasn't clear to you what this means, all I meant was, let's see if we can use the wave function formula. That's the formula for the displacement of the string as a function of x and t. Y max sine of kx minus omega t. We already know the phase angle is 0. And we're saying plug in numbers. So y, the value of y, when x equals 1 meter and t equals 2 seconds is y max 2.5 centimeters. You can leave it like that. That'll just give you the displacement in centimeters. Times sine of, let me use a square bracket, k. Oh, it didn't ask us to find k, did it? But it did ask us to find the wavelength. And remember, k is 2 pi over the wavelength. So for the k, 2 pi, and there's a radian with that technically, over the wavelength, 2 meters. Okay, that's k. The x value is 1 meter, so I have to multiply the k by the x value. Then minus the omega, the angular frequency. They didn't ask me to find that, but I did find the period, big T, and the angular frequency is 2 pi over big T. So let's write that as 2 pi radian over the period, 3 seconds. So that's the omega, and now plug in the t value they gave us, 2 seconds. Let's look at units inside here. Meter cancels meter, second cancels second. The unit that's left inside is the radian. That means my calculator has to be in radian mode. And that's what I'm ready for. I'll just tell you one little thing you can do to simplify this. 2.5 centimeters sine of. I will just tell you that all that argument inside the sine function simplifies to negative pi over 3 radians. You don't have to simplify it, though. What you would do, though, is you go to your calculator. Make sure your calculator is in radian mode. Take the sine of negative pi over 3, and don't forget the negative, and then multiply by 2.5, and that'll be the y value for the x of 1 meter and the t of 2 seconds, and it'll be in centimeters. And I get negative 2 point, let me write that better. Negative 2.17 centimeters. That's the displacement. If we go back and look at our plot, let me get rid of some of that extraneous writing I've put on there. I'm talking about x equals 1 meter. That's actually right there. And t equals 2 seconds, and the y value is negative 2.17. That's talking about that point right there. And if you look about where that is on the y-axis, it looks like it's about at negative 2.17. In fact, this snapshot was taken at t equals 2 seconds. I'm just telling you. Okay? All right, that's some practice. Mostly conceptual. Do you know what the terms mean? Okay? Now let me do a Wiley Plus problem. The Wiley Plus problem is going to focus more on the speed of a transverse wave on a taut string. Okay? And it's going to give us a physical situation where a string, in fact, 2 strings, are under tension, and we're going to have to get the wave speed for waves traveling on those strings. So this is out of our book, Chapter 16, Problem 24. Here's the scenario. In figure A below, we've got 3 pulleys, a big block of stuff, and two strings. String 1 on the left has a linear density, that's the mu, of 3 grams per meter. And string 2 has a linear density, mu, of 5 grams per meter. So string 2 is more dense than string 1. And if I look at my drawing, it looks about right, because string 2 looks thicker than string 1. They're both under tension due to the hanging block, that big old block there, of mass big M equals 500 grams. And the two strings are tied together with a knot at their ends that you can see there. Our task in part A is to simply calculate the wave speed on string 1 and string 2. If I were to, if you like, pluck string 1 and make a disturbance on it, pluck it with my fingers, then that disturbance would travel along string 1, all along it, all down the pulley, over around the vertical pulley, up through the knot into string 2, and over to the other side. And that transverse wave would travel through those strings. How quickly would it travel? Okay? All right. Well, we go straight to the formula for the speed of a transverse wave on a taut string. We'll do it for string 1. Okay? Right then. We'll start with string 1. So we'll call this V1. That would be the square root of the tension in the string, let's call that Ft1, over the mass per unit length in that string, mu1. Where the mass per unit length in string 1 is 3 grams per meter, note, that's 0.003 kilogram per meter, SI. What I need, though, is the tension in string 1. That's what Ft1 means. What is the tension in string 1, which starts on the left, goes around the left pulley, down and completely around the hanging pulley, and up to the knot? What's the tension in that string? It's certainly taut. What's its tension? Well, to answer that carefully and correctly, we're going to have to draw some more free body diagrams. And I'm going to start with a free body diagram for that block, that big block hanging there of mass M. Of course, for a free body diagram, I just represent the block as a particle. Okay, what are the forces? Well, of course, there's F-grav, gravitational force on the block. What else? Please note the only thing touching the block is this segment of string right here. That is not string 1 or string 2. It is a completely different string or rope that they're just using to hang the block from the vertical pulley. I want to emphasize that is not string 1 or string 2. It's just that hanging string or rope. But that's what's touching the block. And so that must exert a tension force. And that must be up. Let me just call that tension force T. And let me apply Newton's second law to the block. A sub y equals F net y over m, where I'll choose plus y upward. Now the block is just hanging there motionless. So it has no acceleration, of course. A sub y is 0. So Newton tells me that F net y must be 0. Since I've only got two vertical forces, F grav down and tension up, their magnitudes must be equal. The magnitude of the tension, big T is what I'm calling it, sorry, must equal the magnitude of the gravitational force on that block. So the magnitude of the tension in that rope is m times g. Again, please note, that's the tension in that rope right there. It's not the tension in string 1, as I'm about to show you. Now the next thing I'm going to do is draw a free body diagram for that vertical pulley. Okay? All right, now, it has that rope pulling down. So that exerts a force, tension force, T. And I already know the magnitude of that from the application of Newton's second law I just did. Whoops, sorry. You can see it. All right. What other forces on the pulley? Well, it's string one. Let's look at that picture again. It's string one that wraps around the pulley, the bottom half of it. It does a 180, goes around the bottom half of that pulley, and then goes up on either side. So string one, which is under tension, is exerting a tension force upward on either side of that pulley. So I have to include a tension force upward on each side from string one, since it wraps around and then goes back up again. So each one of these I'm going to call FT1, because they represent the tension force in string one. Because it is string one that wraps around the bottom half of that pulley, like that. Note, by the way, I'm neglecting any mass of the pulley itself compared to the mass of that block that's pulling down on it. Okay, so now we'll apply Newton's second law to the pulley. A sub y equals F net y over whatever the mass of the pulley is. But A sub y is 0 because that pulley is not moving. So the net y force on this pulley must be 0. I have 2 up forces and 1 down. The 2 up forces have to be equal because they're both tensions from string 1. So 2 times the magnitude of Ft1 must equal the magnitude of T, which is equal to big M times G. So to solve for the magnitude of the tension in string 1, we divide by 2. And we get mg over 2. Note we see a benefit then, and this is one of the reasons pulleys are used. To hold up that block, think of that as the load, which has a weight mg. When I wrap the rope around the pulley going down, around the bottom half and back up, therefore I get 2 upward tension forces from the rope supporting that load. I only need the tension in the whole string 1 to be half the weight of the load. Easier on the string. But that's the tension in string 1, mg over 2, where m's the m of that block. Now that I know that, I can get v1, the speed that a transverse wave would have if we set it up on string 1. That's all they're asking. They're saying if you set up a transverse wave on string 1, what would be the speed of it? And this would be the formula you would use. Square root of the tension in string 1 over the mass per unit length of string 1. But I just found the tension in string 1 is mg over 2. So this is the square root of mg over 2 mu 1. So that's the square root of big M, 0.500 kilograms, times 9.8 Newton per meter, over 2 times 0.003 kilogram per meter for the mass per unit length of string 1. And I get, when I round it to 2 sig figs, 3 sig figs, 28.6 meters per second. That's how fast a transverse wave would travel in string 1. Now let's play the same game for string 2. For string 2, the speed of a transverse wave would be given by whatever the tension is in string 2 over the mass per unit length of string 2. You can't just assume the V's are going to be the same. Now I already know the mu for string 2, that's given. So it all boils down to what's the tension in string 2. Now that takes a little bit of thinking. Because string 1 and string 2 are tied together with a knot at their ends. Now I know what the tension is in string 1. That's determined by that load, that block. But what's the tension in string 2? If your intuition is that the tensions in the two strings are equal, that's correct. Because if the tensions in the two strings weren't equal, then something's going to be moving. But nothing's moving. But let's be a little bit more clear than that. Let's convince ourselves that the tension in the two strings are equal by drawing a free body diagram for, believe it or not, no pun intended, the knot at the ends of the strings where they're tied together. Just treat it as a particle. Let's say that knot has some mass delta m. It's not going to be much. It's not a big knot. What are the forces acting on the knot? Well, it's got the two strings, string 1 and string 2. They're both under tension. String 1's got to be pulling down. So there's Ft1. And string 2's got to be pulling up. Ft2. I'm assuming that the gravitational force on the knot is small compared to Ft1. The knot is not accelerating. So if I apply Newton's second law to the knot, I get F net y equals 0. I got one downward force, one upward force. Therefore, the forces must have the same magnitude. Therefore, Ft2 must equal Ft1. So whatever tension there is in string 1, and that's determined by that load hanging down there, that's the tension in string 2. So we've proved it with Newton. But the intuition is, as I said, if the tensions in those two strings weren't equal, or they were unbalanced, something's going to be moving. But nothing is moving. Okay. So now I use the fact that the tensions are equal. And of course, remember, that's mg over 2. We already found that. So we just plug into the formula for V2. mg over 2 mu2. Notice that the mu2, though, is for string 2. So you can plug in the m and the g and the 2. And for the mu2, you put in 0.005 kilogram per meter. And since string 2 is more dense than string 1, it's going to be more sluggish. It's going to have a slower wave speed. And what you get here to 3 sig figs is 22.1 meters per second. Okay, so a transverse wave will travel at a different speed in the two strings. And that's because they have different mass densities, even though they have the same tension. Now here's part B. Next, the block is divided into two blocks with masses m1 and m2. See them down there in picture B? But m1 plus m2 equals m. You don't lose anything. And the apparatus is arranged as shown in figure B. m1 hangs from string 1, m2 hangs from string 2, and string 1 and string 2 are no longer tied together. They're completely separate. The question is, find m1 and m2 such that the waves in the two strings are equal. If I were to create a transverse wave on string 1 and a transverse wave on string 2, those waves would travel at the same speed. All right, well, let's just write down mathematically what we want. We want V1 to equal V2. I want the V's of transverse waves on the two strings to be equal. That means V1 squared must equal V2 squared. Why did I write it that way? Because then for V1 squared, I can put Ft1 over mu1, tension in string 1 over its linear mass density, must equal Ft2 over mu2, tension in string 2 over its linear mass density. Better figure out those tensions, though. Better do that. I have to do that separately. So let's start by drawing free body diagrams. One for block 1 and then one for block 2. Block 1 has a gravitational force, Fg1, because it's from that part that is mass m1, and an upward force from the tension, Ft1, and those are the only two forces, and they balance. So magnitude of ft1 equals magnitude of fg1 equals m1 times g. And you can come to the same conclusion for block 2, right? Block 2 is string 2, I should say. Block 2 has mass m2. It's connected to string 2. Block 2 is just hanging there at rest. So the downward force from gravity on that block and the upward tension force from string 2 must balance. And you apply Newton's second law, and you conclude that the magnitude of tension 2, Ft2, is equal to the magnitude of F grav 2 is equal to M2G. So each tension is equal to the weight of the corresponding block. So let's put those in for the tensions. On the left, for Ft1, I put in M1G. So I have M1G over mu1. And on the right, I have M2G over mu2. You can divide both sides by G. And then I found it convenient, next step, to rearrange this formula as an equation for M2. Sorry. Okay, I'm rearranging the formula to get an equation for M2. And you get M2 equals, now be careful, you got M's and Mu's. Mu2 over mu1 times M1. Don't confuse M's and Mu's. Mu's are the mass per unit length of the strings. M's are the masses of those blocks. Okay, I'm just going to call this equation 1. That's what I've learned. That's how the masses have to be related if I'm going to have the V's be the same. But let me use, so I need another idea. Well, the other idea is that M1 plus M2 is equal to the total M we started with, and that was 500 grams, or 0.5 kilograms. Now let me just substitute equation 1. That writes M2 in terms of M1. So M1 plus mu2 over mu1 times M1 equals M. Factor in M1 on the left, 1 plus mu2 over mu1. Sorry, I keep doing that. 1 plus mu2 over mu1, close bracket, equals M. So, M1 equals M total over 1 plus mu2 over mu1. Okay? Again, the M total was 0.5 kilograms. And I divide that by 1 plus mu2 over mu1. Here I'm just going to leave them in their original units since it's a ratio. The key thing is that the units be the same. I'm going to express them both in gram per meter. Then those units cancel. And so that is really just 0.5 kilograms divided by 1 plus 5/3. And that turns out to be 187.5, whoops, sorry, 0.1875 kilograms. That's exact, so I'll just write it like that. 0.1875 kilograms. Of course, it's not hard to get M2 once you have M1. M2 is M total minus M1. And that means you have 0.3125 kilograms for the mass of the second block. Okay, so that was working with the speed of a transverse wave on a taut string. And that's all for this video.